All right, today we are jumping into something really fundamental, the language of truth itself. We're talking about mathematical logic. And trust me, this isn't some dusty, abstract topic. It's basically the operating system for how we think clearly.
But, why should we care about all these symbols and rules? Well, have you ever really stopped to wonder how a computer, just a box of circuits and electricity, actually makes a decision? Or, even bigger, how can you or I prove that an argument we're making is actually solid and true?
Well, the answer to both of those massive questions is rooted right here, in what we call formal logic. Think of it as the ultimate toolkit for building ideas and arguments that can actually stand up to being tested. So, let's dive in.
At its very heart, logic is really just a process. It's how we get from a starting point to a conclusion by using a valid reason. It's the set of rules that make sure our thinking isn't just random, but that our conclusions are actually justified.
So how do we start building this whole system of reason? We have to begin with the smallest possible piece, the absolute basic unit, you could say, the atom of our logical language, and that is the statement.
Now, what's really key here is how strict this definition is. In logic, a statement isn't just any old sentence. It has to be something you can declare as either true or false. There's no in-between, no maybe, no gray area.
For example, Delhi isn't India. That's a statement. It's an assertion, and we can check it. And, yep, it's true. But look at the other side. Please open the door. That's a command. You can't say a command is true or false, right? Same thing for a question or just shouting, wow. Logic can only work with claims that have a clear, definite truth value.
Okay, so we've got our basic building blocks, our logical atoms. But, a pile of atoms doesn't really do much. To build bigger, more complex thoughts, we need a way to connect our statements. And for that, we have what are called logical connectives. This is the glue that holds our arguments together.
First up is the one we use a million times a day, conjunction. You and I just call it and. Its symbol looks kind of like a little wedge pointing up. And it does exactly what you'd think. It joins two statements together.
So for instance, we can take the statement, Delhi is in India, and connect it with Mount Everest is the highest mountain. The result is one bigger compound statement, all linked together by that simple word, and.
But here's the rule. When is this combined and statement actually true? Well, this little chart, a truth table, shows us everything. And notice, and is pretty demanding. The only time the whole thing is true is in that very first row when both of the original parts are true. If even one part is false, the whole thing is false.
Next, we have disjunction, which is just the fancy word for or. Now, or is way more laid back than and. If you say something like, it is raining or the sun is out, that's considered true if it's raining, it's true if the sun is out, and it's even true if both are happening at once. The only way it's false is if neither one is true. Then there's negation, or not. This is the easiest one of all. It literally just flips the truth value. So if the statement, the sky is blue, is true, then its negation, the sky is not blue, is, well, false. Simple as that.
Okay, now for the one that can be a little bit tricky sometimes, the conditional statement. This is our classic if-then setup. It creates a relationship where if the first part is true, then the second part is supposed to follow.
And here it is. This is the single most important rule to get about conditionals. An if-then statement is considered logically sound in almost every situation. It is only considered false in one very specific case, when you start with a true if part and it leads you to a false then part. That's the only time logic says, nope, that doesn't work.
And we can see that exact rule right here in the truth table. Just look at that second row. A true hypothesis leads to a false conclusion, and that is the only combination that gives us a false result. Everything else gets a passing grade.
Last but not least, we have the biconditional. You'll hear this as if and only if. The best way to think about this is like a strict contract or a two-way street. The two statements have to have the same truth value. If they're both true, the whole thing is true. If they're both false, it's also true. But if one is true and the other is false, the contract is broken and the statement is false.
So,
We've got our atoms, our statements, and we've got our glue, the connectives. Now we get to do the fun part and see what happens when we put them all together. This is where we start to see these really powerful, almost magical patterns emerge from just a few simple rules.
One of these incredible patterns is called a tautology. This is a statement that is constructed in such a perfect way that it is guaranteed to be true. No matter what, it's impossible for it to be false.
For instance, just think about this sentence. It is a rainy day, or it is not a rainy day. I mean, it has to be one or the other, right? Because we connected these two possibilities with or, the entire statement is just unshakably 100% always true.
And the polar opposite of that perfect statement is a contradiction. This is a statement that's structured in a way that makes it logically impossible. It's built to fail. It is always false.
Just take the statement, I like coffee and I don't like coffee. Because you're using and, you're demanding that both parts be true at the same time. You're claiming two opposite things simultaneously. It's a statement that logically just self-destructs. It has to be false.
And that really is the big takeaway here. We started with these super simple building blocks, things that are just true or false. We added just 5 little rules for connecting them, and with just that, we can create this incredibly powerful system for testing if something is true and for building huge, complex arguments from scratch.
And all of this leaves us with a really deep final thought. We've seen that logic is this formal system of rules. In fact, it's the very language computers are built on. So if that's true, can a machine that perfectly follows all these logical rules ever truly think? Or is there something more to consciousness?